Okay, let's unpack this. When we think about how a computer system performs, how quickly it responds, how many users it handles, we usually think about, well, server speed, network, job sizes.
The usual suspects, yeah.
But what if there's this hidden factor, something about the pattern of how users interact that can just blow up performance predictions? Not just a bit, but like orders of magnitude.
That's exactly it. It's this often invisible thing.
Yeah.
The underlying system model, how you represent user behavior, how new requests get generated. It sounds technical, but this paper we're looking at really hammers home how crucial it is.
Right. So for this deep dive, we're getting into a really insightful paper that highlights this critical difference between open and closed system models and how getting it wrong can totally mess up your performance evaluation, even how you generate test workloads.
Yeah, our mission here is pretty clear.
Yeah.
Break down these models, show you the honestly sometimes surprising ways they behave differently.
And how that affects things like response time, scheduling.
Exactly. And importantly, give you the principles from the paper so you can figure out which model actually fits your situation. Think of it as a shortcut to a really foundational concept in system performance.
All right, let's lay the groundwork then. The paper talks about three main models: closed, open, and partly open. Can you walk us through those?
Absolutely. Let's start with a closed system. Picture this. You have a fixed number of users, always the same number. The paper calls it the multi-programming level, or MPL.
Okay, fixed group.
Right, and they're in this loop. A user sends a request, waits, gets the answer back, and then they, think for a bit before sending the next request.
So thinking is part of the cycle.
Critically, yes. A new request only happens after the previous one from that same user finishes and they complete their think time. It's a closed loop. If you look at Figure 1A in the paper, it shows that cycle explicitly. Job completion plus think time triggers the next job.
Got it. Fixed pool, continuous cycle, thinking time matters. How's the open system different?
Fundamentally different arrival process. Forget the fixed pool. Imagine an infinite stream of new users just appearing over time, independently.
Like people walking up to a counter randomly?
Sort of, yeah.
Yeah.
Each user shows up, submits one job, waits for it, gets the response, and then, poof, they're gone. They leave the system entirely.
One and done.
Exactly. And the key point is, new arrivals are totally independent of whether other jobs are finishing inside the system. Figure 1B shows this arrivals come from the outside world, unrelated to the system's internal state or speed.
Okay, external arrivals, no dependency on completions. And the third one, partly open. Sounds like a mix.
It is. It's designed to be more realistic for things like, websites. Users arrive from outside, like the open model.
Right.
But after their first request finishes, they don't necessarily leave.
Ah, okay.
They might submit another request, maybe a follow-up click on the site with some probability P, or they might leave with probability 1P. This creates sessions. One visit might involve several requests over time. Figure 1C shows that structure.
Right, so you get these bursts of activity from one arrival. So the real pivot point, the core difference, is how new work gets triggered.
That's the heart of it. Closed. Triggered by completion plus think time from a fixed set. Open. Independent external arrivals. Partly open. External arrivals start sessions, but follow-up requests within the session depend on completions.
And that seemingly small difference has big consequences.
Profound consequences, especially when you start looking at performance metrics like response time.
Yeah, speaking of that, the paper just hits you with this finding right away mean response times. For the exact same overall load, they say closed systems are way lower, like orders of magnitude or more. Lower. Figures 2 and 5A show that pretty dramatically, even for simple FCFS scheduling.
It's principle I, and yeah, it's startling. Anyone doing capacity planning needs to see this. The intuition the paper gives is quite neat, actually. In a closed system, you have that fixed number of users.
MDL, yeah.
So at any moment, those end users are either thinking, waiting in a queue, or actually being served. That means the total number of jobs physically in the system waiting or running can never be more than N.
Ah, it puts a cap on the queue size.
Exactly. It's a natural limit on congestion. An open system, no such limit. If jobs arrive faster than the system can handle them, even temporarily, the queue can just grow and grow, theoretically infinitely if it stays overloaded. That's why response times can skyrocket.
Okay. The fix N is like a safety valve in the closed system. Now, the paper does say, okay, if you crank up N, the MPL, in a closed system, it starts to act more like an open one. Principle 2, convergence.
Yes, theoretically, an infinitely large closed system would behave like an open system. But, and this is the crucial part of Principle 2, that convergence is often really slow in practice.
Slow how?
Look at Figure 5A. Even with a pretty high MPL, like 1,000 users, the closed system can still show much lower response times than a comparable open system, especially, and this is key, when the job sizes are highly variable.
Okay, job size variability, that's principle 3, right? High variability hits open systems hard, but not closed systems as much.
Precisely. Principle 3. Let's define variability quickly. They use C2, the squared coefficient of variation of service times. High C2 means you have a mix of very short and very long jobs.
Like quick database lookups mixed with big report generations.
Exactly. In an open system, with jobs just arriving randomly, it's easy for a quick little job to get stuck behind a massive long-running one that absolutely kills the average response time. Figure 5b shows that steep climb for the open system as C2 goes up.
But in the closed system, that doesn't happen as much.
It's dampened. Because you only have n jobs circulating at most, especially at lower MPLs, there are just fewer chances for those short jobs to get trapped behind long ones for ages. Variability still matters a bit, but nowhere near the same damaging effect as in an open system.
So let's connect this back for everyone listening. Why should you care so much about this model choice?
Because it's absolutely critical. The paper points out and shows in Table 1 that a lot of standard benchmarks and tools we use to test performance were built assuming closed models. Think older systems, batch processing, fixed terminals.
Right.
Now, if you take one of those tools and use it to test a modern system that really behaves like an open one, a public website, an API getting random hits, a cloud service, you could be seriously underestimating the response times your real users will see.
And underestimating the resources you need.
Totally. You might think your system is fine based on a closed model test, deploy it, and then it falls over under real open system load. It's a huge potential pitfall in capacity planning.
Wow. Okay. Orders of magnitude wrong. Just from the model assumption. That's huge. All right. Response time is one big area. What about scheduling? How the system decides which job to run next. FCFS, processor sharing, smarter ones like shortest remaining processing time.
SRPT, yeah, or PSJF. Things that try to prioritize short jobs. And guess what? The model matters hugely here too. Well, in open systems, those smart scheduling policies that favor short jobs, they are super effective. They can slash the average response time dramatically, often by large factors. You see that in figures 2 and 6. Getting short jobs out quickly really helps the average when new jobs keep arriving independently.
Makes sense. Clear the decks quickly. But I sense a but coming for closed systems.
You sense correctly. Principle 4 drops the bomb. Scheduling is much less effective in closed systems. Way less bang for your buck compared to open systems. Again, figures 2 and 6 show this stark difference.
But why? Shouldn't ordering jobs always help somehow?
You'd think so, intuitively. But remember that closed loop and Little's law. In closed system with zero think time, Little's law, n equals XET, basically fixes things. N is fixed. Throughput X also becomes fixed because users immediately submit a new job after one finishes. If N and X are fixed, the average response time ET has to be fixed too, no matter how you schedule.
Whoa, okay, zero effect with zero think time.
Zero effect on the mean response time? Yes. Now add some think time, and scheduling can have some effect because think time allows throughput to vary a bit, but it's still heavily constrained by that fixed population N cycling through. The gains are limited.
So the fixed N just dampens the scheduling power. Are there any cases where scheduling makes a real dent in a closed system?
Yeah, Principle V points this out. It can have a noticeable effect, but only under specific conditions. You need moderate to high load think utilization around 0.7 to 0.85, and you need a high MPL. Look at figure 6a. Even then, the improvement might only be like a factor of 2.5 maybe, which is okay, but nothing like the orders of magnitude gains you can see in open systems.
So niche conditions and limited upside. Got it. And how does scheduling play with that job size variability we talked about?
Good question. Principle 6. Scheduling, especially the short job first types, does help reduce the negative impact of high variability, high C2, in both open and closed systems. That makes sense. Prioritizing short jobs stops them getting stuck. You see that in figure 6b.
Okay, so it helps everywhere with variability.
It helps, but again, the improvement is less dramatic in closed systems. Why? Because variability didn't hurt closed systems nearly as much to begin with. Remember Principle 3. So there's less damage for scheduling to fix.
Right, right. Okay, so the big takeaway for you listening here is, if you're testing a fancy new scheduling policy, maybe using a standard benchmark tool that acts like a closed system,
but your real system is open,
you might totally underestimate how good that policy actually is in production. You could wrongly decide it's not worth the effort.
Exactly. The model you test with dictates how effective scheduling appears to be. It's fundamental for evaluation.
Okay, we've hammered on pure open and pure closed. But you mentioned the partly open model earlier, the hybrid one for things like websites with sessions. How does that fit into this picture?
Right. The partly open model tries to be more realistic.
Hmm.
And Principle 7 tells us how it behaves.
Yeah.
Its performance, its response time, its reaction to scheduling, it all falls somewhere between pure open and pure closed.
A spectrum, then.
Exactly. And where it lands on that spectrum depends mainly on one thing: the average number of requests a user makes per session.
Ah, how long they stick around clicking things.
Precisely. The paper offers a great rule of thumb. If the average session length is short, say 5 requests or fewer, the system acts pretty much like a pure open system.
Makes sense, like lots of quick, independent visits.
Yep. But if the average session length is long, say 10 requests or more, it starts to behave much more like a closed system.
Because users are sticking around, interacting repeatedly, creating that feedback loop implicitly.
I got it. Figures 2 and 8AB illustrate this transition really well. The exact crossover point, whether it's 5 or maybe closer to 20 requests, can depend a bit on job size variability, C2, but the principle holds. Session length is key.
Okay, that's a super useful guideline. Now, there was something about think time within the session in this model that seemed odd.
Ah, yes. Principle 8.
Hmm.
This one trips people up. You'd naturally think, okay, if users pause longer between clicks within their session, that spreads out the load, right? Should improve things.
Yeah, seems obvious. Less load, better response time.
But the paper finds, counterintuitively, that the average think time between requests within a session has very little effect on the overall mean response time or system load. Look at figures 8C and 8D.
Wait, really? Little effect. Why wouldn't pausing help?
The explanation is that if the rate at which new sessions arrive is fixed, and the average number of requests per session is fixed, then the total amount of work hitting the system over time is basically fixed too. The think time just changes when exactly the requests within a single session arrive, adding some small correlations. It doesn't change the overall demand significantly.
So it's the session arrival rate and the total work per session that dominate, not the pauses within.
Exactly. To really impact performance in a partly open system, you need to change how often new users arrive or how much total work they do per visit, not just how long they pause between clicks during that visit.
Okay, that's crucial for modeling. Focus on session arrivals and session length. Don't sweat the intersession think times too much.
Saves a lot of modeling effort potentially, yeah.
So we've seen these models are fundamentally different, behavior shifts. It all comes down to the practical question. How do you actually use this? How do you pick the right model when you're looking at your real system, your website, your API?
And that's the million-dollar question, right? The paper stresses, again, you have to choose the appropriate model for accurate results. It lays out a pretty logical process, especially for web-type workloads. Step 1, get real data. You need traces of actual user interactions. No guessing.
Ground truth first.
Always. Step 2, analyze those traces specifically to build a partly open model view. The absolute key parameter you need to extract is the average number of requests per user session.
How do you define a session in the trace?
Typically by grouping requests from the same user that occur within some time threshold. Like if a user is inactive for, say, 30 minutes, 1800 seconds is common, you assume their session ended. You do this across your trace data and calculate the average number of requests before such a timeout. Table 2 and Figure 9 in the paper show this analysis for real sites, and importantly, they show that average session length varies wildly between different sites.
So you measure the typical request per visit for your specific workload.
Exactly. Then step 3, use Principle 7, that rule of thumb about session length, as your guide. If your analysis shows users average, 2 requests per session, Principle 7 says an open model is probably a decent approximation.
Okay.
If they average 15 requests per session, a closed model might be closer to reality. And if it's in that fuzzy middle ground, maybe 5 to 10 requests, you really need a proper partly open model if you want accuracy. The paper gives examples. Site 6 acted open, Site 10 acted closed, Sites 3 and 7 needed the partly open view.
And this matters hugely because, going back to Table 1, most standard workload tools only do pure open or pure closed.
Right. That's the practical constraint often.
Okay.
You might not have a perfect partly open generator. So you use your session length analysis in Principle 7 to make the most informed choice about which available model, open or closed, is the least bad approximation for your specific reality.
Gotcha. The principles guide your choice even with imperfect tools.
Precisely.
Okay, this has definitely been a deep dive. We've really seen that this choice, open, closed, partly open, it's not just some minor technical detail. It fundamentally changes your performance numbers, your response times, how effective you think things like scheduling are, sometimes by massive amounts.
Yeah, to quickly recap the core ideas, closed systems often look faster, scheduling often looks less useful compared to open systems, mainly due to that fixed population feedback loop. Variability hurts open systems way more,
Partly open bridges the gap.
based almost entirely on that average session length. Short sessions act open, long sessions act closed. And remember the weird one, think time within a session. Surprisingly unimportant compared to session arrival rate and length.
And it all points back to analyze your real workload first to figure out which model actually reflects how users interact with your system before you trust any performance numbers.
It's step zero, really, the step people often skip.
Which leaves us with a final thought for you listening. Given how profoundly this model choice impacts results, potentially leading to underbuilt systems or dismissing good optimizations, why do you think this distinction is so often overlooked or ignored in practice? What are the potential real-world consequences if the performance studies and capacity plans we depend on are built using models that fundamentally mismatch reality?
It's a significant blind spot in the field, for sure.
Something to chew on next time you see a performance graph or a capacity claim.